with the last main topic of the first year work, which is chemical equilibria. I'm going to divide into 3 or 4 videos with one of the topics, which is equilibrium constant. I'm going to leave to the end and only do that video if there's time available, because we do this again in the second year and do it in more detail. So the first one I'm going to do is look at what we mean by equilibrium and what we mean by dynamic equilibrium and also position equilibrium. Chemical equilibria relates to reversible reactions, and you probably can see from the word equilibria it is related to the word equal, and that's because in a reversible reaction an equilibrium is reached, or equilibrium is when we have the rate of the forward reaction equals the rate of the reverse reaction. So for example, I've chosen here a reversible reaction of dinitrogen tetroxide, NCO4, decomposing or breaking down to nitrogen dioxide or 2 lots of nitrogen dioxide, NO2. Now I've chosen this reaction because there's only one reactant and one product, so it's simpler to understand. Dinitrogen tetroxide is a colourless gas and nitrogen dioxide is a brown gas, so you can monitor this reaction using a colorimeter. So let's look at what happens to the rate of the forward and reverse reactions over time. So let's assume we start with no nitrogen dioxide and we only have dinitrogen tetroxide. So let's look at the rate of reaction with the dinitrogen tetroxide. The rate of the forward reactions can be very high at the beginning because we've got very high concentration of the reactants. So we're going to have it around here. And the rate of the nitrogen dioxide reacting back to form the dinitrogen tetroxide is going to be 0 because there's no nitrogen dioxide at the beginning, so the rate of the reverse reaction can be 0. So for the reverse, it's going to be 0, which is here. The rate of reaction is going to be quite high at the beginning for the forward reaction because we've got relatively high amounts of the dinitrogen tetroxide, and as this reacts away, the concentration of this is going to decrease, so the rate is going to decrease for the forward reaction. As the forward reaction occurs, the concentration of the nitrogen dioxide will increase, and therefore the reaction going backwards, the reverse reaction, will start to occur, and the rate of the reverse reaction will start to increase. So we will see this happening. Over time, as the concentration of the dinitrogen tetroxide decreases, the rate is going to decrease, and over time, as the amount of nitrogen dioxide increases as it's made, the rate of the reverse reaction is going to increase, and eventually when the rate of the forward and reverse reaction are equal, we have by definition chemical equilibrium. Be careful when you read this graph, as this is not the amount of the dinitrogen tetroxide decreasing, this is the rate of the reaction, of the forward reaction, and this is not the amount of the nitrogen dioxide, this is the rate of the reverse reaction increasing. We can look at a different graph to show the change in the amounts of these, or concentration of these over time. So let's look at the graph to show the change in concentration of both of these, and let's start with dinitrogen tetroxide. I'm going to start high concentration of this because we have none of the nitrogen dioxide and only the dinitrogen tetroxide. At the beginning of the reaction, we're starting with no nitrogen dioxide, so that will be 0. Over time, the concentration of this is going to decrease, and as the dinitrogen tetroxide converts to the nitrogen dioxide, the concentration of the nitrogen dioxide is going to increase. You may want to think about why this increase here is bigger an increase than this decrease here. So you can pause the video and think about why that is. Hopefully you spotted the stoichiometry, and this would explain the difference in an increase compared to the decrease of these two graphs. So on this graph, where is equilibrium? Is it going to be here? Is it here where they meet? Or is it elsewhere? Well, equilibrium is when the amount of these two are not changing at all. So that is at around this point here, when there's no change in concentration of either of these. So here the nitrogen dioxide is not changing over time, and here the dinitrogen tetroxide is not changing over time. So at this point in time, that is when equilibrium is reached. You notice at equilibrium the amounts of the two substances, or the concentration of the two substances, are not equal. They don't have to be equal. In this case, at equilibrium, we got more of the nitrogen dioxide than we have the dinitrogen tetroxide. The concentration of this is actually higher than the dinitrogen tetroxide. We use the term position of equilibrium to describe the relative amounts of the reactants and products in a reversible reaction at equilibrium. And in this case, because the concentration of the nitrogen dioxide is greater than the concentration of the dinitrogen tetroxide, we say that the position equilibrium for this reversible reaction is further to the right hand side. So as we said earlier, at equilibrium, the amounts of the reactants and products may not be equal, or the concentrations of the reactants and products may not be equal. So equilibrium means the forward rate of reaction and the reverse reaction rates are equal, but not the actual amounts of the substances, which is a common misconception some students have. So you could have an equilibrium where you've got a lot of the reactants on the left hand side compared to the products on the right hand side of the equation, or vice versa. So we use this term position equilibrium to describe the relative amount of those reactants and products at equilibrium. So the position equilibrium is a term that tells us the relative amount of reactants and products in a reversible reaction at equilibrium. So for example, we have the Haber process, and at equilibrium we have more of the ammonia present compared to the nitrogen and hydrogen gases. Then we say that the position equilibrium for this reaction is towards the right hand side of the equation. The position equilibrium isn't fixed, it depends on the conditions of the reaction, and we look at that when we look at Le Chatelier's principle in the next video. So you could have a situation where a reaction mixture of nitrogen, hydrogen and ammonia, you have more of the nitrogen and hydrogen compared to the ammonia, then we say the position equilibrium is towards the left hand side of the equation. I'm going to go back to position equilibrium later, but before we do that I want to talk about dynamic equilibrium, what dynamic equilibrium is, and you need to know 3 features of dynamic equilibria for the exam. Chemical equilibria are said to be dynamic as the forward and reverse reactions are still continuing. So even though the concentrations of the reactants and the products are not changing over time, this isn't due to the fact the reactions have stopped. The reactions are still continuing, going forwards and going backwards, but the forward rate is equal to the reverse rate. So this is different to a static equilibrium where things stay still. So balancing something is an example of static equilibrium. The downward and upward forces on the dog biscuits are equal, so there's no overall movement. The dog and the biscuits are staying still on the left, so it's a static equilibrium. Whereas an example of a dynamic equilibrium could be running on a treadmill, where your forward speed is equal to the reverse speed of the treadmill, so there's no overall movement, but you're still moving and the treadmill is still moving, so it's dynamic. There are 3 features of a dynamic equilibrium, and the first one is an obvious one, which is the rate of the forward reaction must equal to the rate of the reverse reaction. If that doesn't happen, we don't have an equilibrium, because if the forward reaction rate is faster than the reverse reaction rate, it would not be an equilibrium because the rates are not equal. The second feature of a dynamic equilibrium is that it must be a closed system. So what I mean by a closed system is that there's nothing entering or leaving that system or that container. So no reactants or products enter or leave the system. If you start adding reactants to the container, that would increase the rate of the forward reaction. And if you add the product side substances to the container, that will increase the rate of reaction of the reverse reaction. So therefore the forward and reverse rate of reactions won't be equal, and therefore won't have a dynamic equilibrium. The third feature of a dynamic equilibrium is that we must have physical properties being kept constant. So things like temperature or pressure for gases must be kept constant, because those conditions can influence which reaction is favoured, whether the forward reaction is favoured or whether the reverse reaction is favoured. So some conditions are favourable for some reactions and others are favourable for other reactions. So for example, if you've got a reaction involving gases, increasing in pressure will favour the reaction that reduces the total number of particles of gas to reduce the total pressure. And we'll look at this in the next video when we look at Le Chatelier's principle. So going back to position equilibrium and linking it with dynamic equilibrium, here we've got a scenario of you walking up the down escalators. So when you were a child, you may have walked up the down escalators, maybe at a shopping centre or shopping mall. In doing that, you may have set up a dynamic equilibrium where you're constantly walking upwards as the escalator is constantly moving downwards. The constant movement means it's dynamic, but your upward speed equals the downward speed of the escalator, so there's an equilibrium. And the position you are on the escalator is a bit like the position of equilibrium. You could have reached equilibrium near the bottom of the escalator, or if you walked up really quickly at the beginning, you could have managed somehow to reach the top of the escalator before tiring and slowing down to match the speed of the down escalator and reach equilibrium near the top of the escalator. But in the case of a reaction, the position equilibrium isn't where you are on the escalator, it is the relative amount of the reactants compared to the products. So you can have an equilibrium, i.e. where the rate of the forward reaction is the same as the reverse reaction, but we can have the position equilibrium towards the left-hand side as in this first scenario here. So in the reaction mixture, there's more of the reactant side substances compared to the product side substances. So if the position equilibrium is towards the right-hand side, what we mean by that is when the rate of the forward and reverse reactions are equal, so we've got equilibria, we've got more of the product side substances compared to the reactant side substances. So we say the position equilibrium is towards the right-hand side. So we covered what we mean by chemical equilibrium. We define the features of a dynamic equilibrium, and we also explain what we mean by position equilibrium.